So I'll figure out how to do this better, because right now, I guess I'd like it to be a little bit bigger on the screen rather than you seeing like the Google Meet version of my screen. But this is as good as I can do for right now. Welcome to Thermodynamics. So we're going to be going through, talking about thermodynamics in this class. I'm excited. I like teaching this course. I think it's a fun course, and it's one that I think has, hopefully you'll see, it has a lot of connections to a lot of different areas. We're going to look at one little subset of thermodynamics, right? Some of kind of the foundational material, but thermodynamics is a lot bigger than what we're going to be able to cover in 1-2 credit class. But hopefully it gives you at least a taste of the kinds of things that thermodynamics can help us think about, and the kinds of, I guess, the kinds of thought processes that go into thinking about a problem in kind of thermodynamic terms. So we're going to go through, and we'll have a lot of time, more than any of us would like, to go through like how does the course run and how does all that stuff happen. So we'll go through that this morning, or this afternoon. I guess it's 1:30. We'll go through that this afternoon, but before we do that, I just want to start and just kind of dive in a little bit. Try to give us some background of thermodynamics and what it is and why it matters and why maybe why I care and why maybe you should care. So this guy up here is somebody that none of you have ever seen before, and I'm almost certain that nobody knows his name. Does anybody know this guy? If you do, that would be kind of a problem. You probably won't, at the end of this class, you still won't know this guy, but you'll at least know his last name. And I put him up here because he played a relatively early role, at least, in taking thermodynamics from kind of a conceptual field, which really has its roots back in the ancient Egyptians and the Greeks, and people were thinking about how does energy work. And he really took it and started to quantify and codify thermodynamics, and really took it and made it more of a quantifiable science, more like an engineering. Can anybody guess from the title? This is an influential book that he wrote in 1824. Can anybody guess from the fact that it was 1824 and that's the title of his book? What was he thinking about? Steam engines. So I think it's interesting to note, like, when did thermodynamics kind of become a thing? Well, it became a thing in the early 1800s, the Industrial Revolution. Why? Because people were thinking about steam engines. And what they were thinking about is, how can we use heat and turn it into something useful, turn it into motion? Right? This is something we still use all of the time. All the time. Right? We don't think about it as much. We don't use steam engines all the time. But we use heat and turn it into motion or some other form of energy all the time. This is, don't quote me on this, but I read somewhere recently, and I didn't check it, so it might be wrong, but something like 90% of the energy that we use is in the form of heat. Right? We're using heat for industrial processes, or we're using heat in a power plant to create electricity, or we're using heat in your car to help your car move, or we're using heat to run a chemical reaction to make something. We use heat all of the time. So the heat aspect of thermodynamics is still important. Okay, so this is, I guess I'm over here. I have to figure out how I'm doing this. I'm running my PowerPoint off here. Okay. No, I don't want that. So so this guy who started kind of really codifying thermodynamics, his name is Nicolas Carnot. He was a French guy. He went to the École Polytechnique in France around the same time that a guy named Ampere also did. You may have heard of him. So that's kind of the time period that we're talking about, when early Industrial Revolution. You can see he died in 1836. He died of cholera. So we're all glad that we don't live in the early industrial revolution. It was not always a happy place. Since then, thermodynamics, like I said, it started kind of looking at steam engines. I would guess that none of you, unless you're like my 7-year-old son, none of you are super excited about steam engines. You're not becoming engineers because you're like, oh, I want to drive trains. Right? We're not here to be that kind of an engineer. I don't know, maybe you are. If so, it's probably not the right spot. But thermodynamics has it's grown a lot since then, right? Those are its roots. That's not what it is today. Although some of the stuff that we'll talk about in this class certainly relates to some of those early roots. But this is just kind of a snapshot of, I'm breaking things. No, I don't want to zoom in. Don't do that. Don't do that. I want a pen. There, do that. So this, bear with me, guys. So this is kind of a snapshot of a brief history of thermodynamics as taken from a screenshot of Wikipedia. This is where all good research starts. But I like it just because it puts some dates on, so it gives you a little flavor of how this has developed over time, but also shows you a little bit of the diversity of thermodynamics. So there are some fun ones in here. Right, ecosystem thermodynamics. This is fun, relativistic thermodynamics. So if you want to learn about relativity, there's some thermodynamics things like the thermodynamics of black holes. If you want to learn about what happens to energy in black holes, that's a thermodynamics type thing. Right, fun one, drug receptor thermodynamics. If you want to look at what's happening in, say, like drugs binding to a certain binding site on, say, a protein or somewhere in the cell, that would be a thermodynamics type problem, or thermodynamics would help you understand that. Earthquake thermodynamics, right? Things that deal with energy, just kind of more generally. Those are thermodynamics type things. My background, so I've been at Hope now since 2018. The research that I do here at Hope and the research that I did before I came here has been in solar energy, right? Taking light and turning it into electricity. If you want to learn what's the best solar cell you could possibly make, thermodynamics. You can do a thermodynamic analysis and see. We'll do that in this class. It'll take us about 2 minutes once we learn how. It's really easy. And that's like, this is the international speed limit of thermodynamics for a solar cell. And if you break that, you broke physics. So that's kind of just to give you a little sense of the types of things that you can be looking at with thermo. So obviously, right, each of these little bullet points is a course or multiple courses or a PhD or something like that. So we're not going to get into all of these, but hopefully it gives you a sense. Right, we're covering a little snippet. Right, this is applied thermodynamics, kind of a short introductory course, but thermo is much bigger than this. And I think you'll see it touches on things that you find interesting. Whether or not you find steam engines interesting is kind of a secondary thing, right? We'll talk a little bit about steam engines, probably more than most of us would like. We're not actually going to be talking about trains, but some of these kind of basic engines and stuff we'll talk about quite a bit. But part of that is kind of in this broader context. So I want to give you a little bit of a flavor for that. Okay. All right. So again, we're just kind of stick with this introduction. We're going to do a thought experiment. Okay, and I apologize, it's not the most complicated thought experiment, but we're going to go through and just bear with me and play along. So let's imagine. Okay, that's relatively small. I'll draw it a little bigger. Okay, so we have a bucket. This bucket has 1 kilogram of water in it. And we're going to add, we have a second bucket that also has 1 kilogram of water. Right, we're going to put those together into a little bit bigger bucket. And let's put some temperatures. So this is 10 degrees Celsius. This is, say, 90 degrees Celsius. When we add these two buckets of water together and pour them into the second bucket, how much water are we going to have by mass? 2 kilograms. Good. How did you know that?
1 plus 1.
Okay, but how come not 1.5 kilograms? Because of conservation of mass, right? Because you believe, you've been told and you believe from your own experience that conservation of mass is a real thing. So if I take 1 kilogram and 1 kilogram, that's 2 kilograms. What's the final temperature? Yeah, Chris? 50 degrees Celsius. I agree with Chris. Chris, how did you know that? Yeah. Conservation of energy. Right, so conservation of mass is something that, again, from what you've learned and from your physical experience, that's a real thing. We're going to be talking a lot in this class about conservation of energy. We kind of did a little bit of hand waving because we have like heat energy. We'll learn to call it heat energy, and we kind of like substituted that for temperature. We do that a lot in our day-to-day speaking of how we talk about heat. If something has a high temperature, that's hot. Heat and temperature are related, but they're not exactly the same thing. So we have to be a little bit careful on kind of like how we typically talk about temperature and how we're going to talk about heat specifically here. But like Chris said, we can think about this. This is conservation of energy. And we could think about it, right? So this guy gains 40 degrees C. This one loses 40 degrees C. And what you kind of intuitively think from the system is that the amount of heat gained by this one is equal to the amount of heat lost by this one. And that's how you end up at 50. Right? That gaining 40 degrees C in temperature is the same amount of heat as losing 40 degrees C in temperature. Okay. So again, bear with me. We'll do another one. So this we have, again, our 1 kilogram of water. It's at 10 degrees C. And now we're going to add to it a a 1 kilogram chunk of copper. And this is 90 degrees C. Okay, so we'll add these together. They go into our thing. Okay, and now we have, if I could draw, we have our 2 kilograms in total mass, just like before. We have 1 kilogram of water, 1 kilogram of copper. We drop them together. We're going to take votes on this. So you're required to answer. You get negative points if you don't answer. I'm keeping track. No. Okay, you're required to answer. What's the final temperature? Is it exactly 50 degrees C still? Raise your hand. Exactly 50 degrees. Is it more than 50 degrees? Okay, more people. Is it less than 50 degrees? Okay, does anybody want to explain why they thought what they did? Remembering that wrongness is great. Anybody? Yeah.
Materials have like specific heat, I think is the word, where it's like it can change temperature faster is how I think of it, and I think water has a higher specific heat than copper. So the copper will change temperature faster than the water.
Yeah. Okay. So this is kind of getting at what. So what Chris is saying is that there's like how fast things change temperature is maybe different. So this is kind of getting at the root of how temperature and heat are not the same thing. So the real answer, for those of you who said less than 50 degrees C, you were correct. The real answer is something like 17 degrees, which I don't know, is that surprising to anybody that it's that low? You mixed like a kilogram and a kilogram, and instead of being like, it's not even close to the average, you just went up 7 degrees instead of 40. But I probably don't have to try super hard, and I can convince you that some of the same things that we said in the first case, in the top case, would still apply in the bottom case. But in the top case, we said that, right, that this one gains some amount of heat, right? Kind of a proxy for that is temperature. It gained 40 degrees Celsius. This guy lost 40 degrees Celsius, and that those were equal and opposite. So we could do the same thing here. So this one gains so it would be 7 degrees C. This one loses, what is that, 73 degrees C. So it's a 10-time different temperature change, but the amount of heat gained by the water is still going to be equal and opposite the heat lost by the copper. Right? We would still all agree with that last sentence. This one here, that the heat gained by the copper is equal to the heat lost by the, or the heat lost by the copper is gained by the water. I probably don't have to try too hard to convince you of that. Okay, so why did we do these two different examples? Well, thermodynamics is the study of, right, thermodynamics, thermal heat dynamics, movement or flow. So one of the things that thermodynamics is, if we want to give it a definition, it's the study of the flow and conversion of energy. And a significant part of that, right, we'll talk about a lot, is heat energy. We'll also talk about mechanical energy. We could talk about electrical energy. We could talk about chemical energy. We can talk about different forms of energy. They would still fall under this umbrella. In this class, we're going to be specifically looking at thermal energy and mechanical energy. Those are kind of the two that we'll focus on, although there are other forms of energy that you all know of. And I think this top example gives, right, it's so easy, but it also gives kind of a framework for how we can think of some of the basics of thermodynamics. Okay, so before we go on, there are kind of three, I have three subpoints kind of within this, the study of energy flow and conversion. There are kind of three different aspects to that. So the first would be energy conversion itself. Let me blow that up a little bit. So energy conversion. So it's the study of energy conversion. So energy conversion is important in that. We'll spend a lot of time talking in this class about that. The second important aspect, which again we'll spend a lot of time, is physical properties. So we have to know things about how water behaves and how copper behaves and how steam behaves and when water turns into steam and back and forth. We have to know about physical properties of matter because that's how energy moves from one place to another, right? You can transport thermal energy from this side of the room to the other side of the room if you carry a hot bucket of water, like from one side to the other. And if you want to know how much, you better know how much thermal energy is in that water. So physical properties. The last one is when things are not flowing. Which are like equilibria processes. We'll close that. So these top two, energy conversion and physical properties of materials, that's where we're going to spend our time this semester. We're not going to touch on equilibrium. That's a part of thermodynamics and a relatively large part, but that more would be covered in like a chemistry class or a biology class, more so than an engineering class. So we'll focus on these top two. How do we convert energy from one kind into the kind that we want? And we do that a lot with materials and with matter, so then we have to know a little bit about the stuff that's actually doing the work, the matter. Okay, so let's come back to our two little examples. So there are, in thermodynamics, there are two, what we call the two laws of thermodynamics. And I think you can see both of them from the assumptions that we made together, kind of behind these kind of our thought process, I guess. So in the first case, we said that the amount of energy, the amount of heat gained by this bucket, right? The temperature goes up, it's gaining heat, is exactly equal to the amount of heat lost by this bucket. And it would be absolutely ridiculous if I said, well, no, really it's not 50 C. The final product when we add these two together is 100 C because 10 plus 90 equals 100. Right? That's obviously not the case because they would both be gaining heat, and where did that heat come from? So kind of like mass, right? If we added 2 kilograms and 2 kilograms, you don't get 3 kilograms because mass is not created or destroyed. Energy is the same way. So the energy has to come from somewhere and it has to go somewhere. So the first law of thermo, these are the laws. The first law of thermo is conservation of heat. I guess in the example that we did, we said heat was conserved, that heat had to go somewhere, that the amount of heat gained by one was equal to the heat lost by the other. But really it's more general, really it's energy. Okay. And that's really the first law of thermo, is a conservation of energy. That energy has to go somewhere. It doesn't appear magically out of nowhere, and it doesn't disappear magically. Maybe it's converted. Maybe it goes from one material into another material, but we can account for it. It has to go somewhere, just like mass does. Okay, the second law again, if we go back up to here, this is really an assumption that we made. It's an assumption that's right? It was true. But it's kind of right, when we're thinking about this problem, it's an assumption that we make because it fits with our everyday experience and we've never seen it proven wrong. When we added the 10-degree water to the 90-degree water, we got something in the middle, 50 degrees. When we added the 10-degree water and the 90-degree copper, we got something in between those, 17 degrees. And you never even thought for 1 second that wouldn't be in between those two. Right? We can't add 10-degree water and 90-degree copper, and the water goes to 0 degrees and the copper heats up to like 150 degrees. Right? That doesn't happen. It's never happened in your experience. When you put a pan of water on the stove, the water doesn't freeze and like the burner on your stove get hotter. It goes the other way, like the heat goes from the stove burner into the water, and that's the way that it always goes, and it's never going to go the other way because it can't. That's the second law. Right? It seems like almost so silly. Why would you even write it down? But this is the fun one. When we do, so we'll do first law stuff. The first law is fairly easy to get a handle on, right? We do balances just like you would do mass balances. Energy balances are more fun because you can change from one kind to a different kind, and it's a lot of fun. The second law, heat only flows down temperature. It only flows one way. It can't go the other way. If you have a hot thing, the heat's going to go from the hot thing into the cold thing. It's not going to go from the cold thing back into the hot thing. That doesn't ever happen. The one kind of place where that can happen is like a refrigerator or an air conditioning unit. Right, in a refrigerator, the cold part gets colder, and your kitchen, the hot part, gets hotter. So that's the one place where it kind of happens, but that only happens because we have the refrigerator plugged in. It doesn't just happen spontaneously, and it never will, and it never has. That's the second law of thermo. And the second law is, that's my favorite of the two. We'll go and we'll put a little bit more definition onto these laws. But what they really are is they're kind of like, these are our operating assumptions that are always true because this is how we've always experienced the world. And right, energy doesn't just disappear, and heat only ever flows one way. But the consequences of these laws are rather profound. There are a lot of different consequences to those. So those are the two laws of thermo. Let's take a little step back and talk a little bit about this specific course, rather than just kind of talking more broadly about thermo. So I think, well, I guess let me do, Okay, so I'll pull up the course Moodle page and we'll walk through some of the stuff that's on there so you can get a little bit of a sense of how this specific course is going to go. If we can load the Moodle page. Come on, buddy. Okay. So on the Moodle page, I'll pull up the syllabus here in a second. What you'll find, though, just the first thing to know, one of the reasons why I'm messing with all this stuff for the recording is if any of you or somebody in the other section misses class for some reason, I'll be recording this lecture. I'll do a better job of it in the future. But you'll have the recording so that if you miss class, you can watch that later. If you want to see something again, you can watch that recording. You can watch that later. You can also join right here at the top, this virtual lecture, Thursdays at 1:30. That's the Google Meet link. So if you ever want to join in live so that you can ask questions, things like that, you can ask questions through the chat on Google Meet, or you can pop in live and ask questions live and everybody can hear you. You can do that just through this, this link. So if you can't make it to class for whatever reason, this is the way that you can attend remotely. Pull up the syllabus here in a second. Okay. So this is the syllabus. We're over here, 340, section 3. We're in SCOP 1008. Looks like everybody found it, despite the fact that, I don't know, this, to me, it took me a long time to find this room the first time. The textbook that we have, right, this guy, I think most of you probably have it as a digital textbook, would guess. If you haven't got this yet or had some hiccup with it on the bookstore, hopefully you can get that resolved in the relatively near future. But the first homework set, which I'll talk about, I guess, in a second, I'm getting ahead of myself. The first homework set is going to be problems from the book, but I have those like scanned and posted on Moodle. So you have a little bit to make sure that you can figure all the book stuff out. But that's our book. We're going to be jumping a little bit around from like section to section. We're not going to be following it like chapter 1, chapter 2, chapter 3. We'll be like chapter 2, chapter 4, chapter 9, chapter 7. We kind of jump around a little bit. But hopefully we can stay. I like the book. I think it's a pretty good book, but we'll be kind of jumping around and doing things out of order from how they do it. No, I can't. Okay. So what we're going to cover in the course, the learning objectives and or the objectives and learning outcomes. We're going to be talking about thermodynamic properties. We're going to be talking about energy conversion, and we're going to be doing that a lot in the context of what we call thermodynamic cycles, which are, again, things that we see in a lot of different places, like the refrigeration cycle or the cycle of your internal combustion engine, or a coal power plant or a natural gas power plant. So some of these systems, and you'll get to understand what we mean by a thermodynamic cycle, but we'll be analyzing and looking at energy conversion processes in the context of cycles a lot. And hopefully, right, this last one here, hopefully you get a sense of how we can use this kind of the concepts of thermodynamics, right, which are just two: energy is not created or destroyed, and heat flows one way. How these can help us understand a broader set of engineering problems, and right, that slide that I showed, which had a whole bunch of different fields, how those two kind of fundamental ideas can be useful in all of those different fields. The actual grading for the course, spend a little bit talking about this. So the percentages, right, is split between like homework and quizzes and the final and midterm, per usual. What I'm going to try to do in this course, and I will do a mediocre job, but it won't be terrible. I'm going to try to make a point worth a point worth a point. So if you, for example, lost 5 points on a quiz and lost 5 points on an exam, those are equivalent to your final grade. So it makes things a little bit weird where like the midterm is worth 250 points, because that's right. 25% of your grade for our one exam is not crazy, but usually it would be worth like 100 points. But this way, like 5 points on the midterm is the same as 5 points on a homework set, is the same as 5 points on a quiz, is the same as, right, you get it. So I'll try to do that. I'll do an okay job. So the brackets, or the parentheses next to it say about how many points total are in that category. So they're going to be about 1,000 points total, right? So if you wanted to get a 93, you can lose 70 points. That's kind of your budget. So, right, you can get maybe an easier sense of where you stand in the class and how different things affect your grade. So hopefully it makes it easier to just kind of at least ballpark how things are changing your grade. That's what I'm going to try to do. The actual final grade will be calculated based off the percentage weighting, but I'll do a pretty good job of keeping the points consistent. As I said, the recording, so there will be a recording which will be of this class. You can either hop in live through the Google Meet link, or you can watch it later. The recording will be posted to Moodle. Homework assignments, typically they'll be assigned weekly. And I'll show you, so let me hop out of that a second. I'll show you what the homework assignment for next week looks like. Right, this will be, so homework number 1, I'll typically have in parentheses when it's due. So this is due 8/27, which is a week from today, due at 9 p.m. That 9 p.m. is intentional. The help sessions for this class are Tuesday and Thursday from 7 to 9. So there's a help session tonight, right? There's a help session next week, Thursday, from 7 to 9. If you have one last question that you weren't sure how to attack this problem or something like that, this gives you time to go to the help session, ask kind of your one last question, and still get the homework in as it's done, and not, hopefully that all works out relatively well. The homeworks are, if you click on the assignment, there's a PDF of, I'll pull it up here a second. There's a PDF of the homework problems, either the numbers, so if they're just numbers like this, these are the numbers for the textbook problems. Sometimes there'll be like the numbers and a hint, or just a written problem, different things like that, but they'll be in this document. So you can go in the assignment link, pull out that document, and then whenever you're done with your homework, upload to this assignment. You're going to submit it in as a PDF, as a single PDF. I think I've restricted it so that you're only allowed to upload a single PDF file. So just take pictures with your phone, use like Genius Scan or some other PDF scanning software. If you have issues with that, let me know and we'll get them hopefully ironed out relatively early in the semester. Okay, let's hop back in the syllabus. Try not to take too much longer on this. Okay, you'll see here I have some formatting guidelines specifically for homework sets. So take a look at those before you try to complete your homework. Quizzes, they'll typically be, so I say like 5-10 minutes. They'll be timed, but I'll give you more than 5 or 10 minutes. So the first quiz, I would say would probably be like, I would estimate 5 to 7 minutes, but you'll have 15 minutes to do it. So you'll have a little bit more time than what I say here. There'll be 15 or 30 points. So we have 100 points total, so that means we'll have like maybe 4 or 5 quizzes throughout the semester. The quizzes will all be given through Moodle, and you'll have 24 hours to actually take it, but it'll be timed once you start. So the quiz will be, right, there's a quiz, let me leave a second. Right, you can see here, this is how I'll usually say it in class, but also I'll announce it on Moodle like this. So this is the block for everything from week 1 is under this week 1 heading, and quiz next week. So that'll be like, okay, there's a quiz coming next week. It's not open yet because you can't take it till next week, Thursday, but it'll be open all day Thursday from, I guess, like, 1 in the morning or 12:01 to 11:59. It'll be open the entire day. But once you start, it'll be timed. So whenever you're going to start the quiz, whenever you have a chunk of time, make sure you're going to sit down and take it from start to finish. If you have a hiccup with that or something, shoot me an email, get in contact. We'll try to make sure to work everything out as far as that goes. Okay. Okay, so I guess the other thing I should have talked about before I jump back in here. Okay, so right, you'll kind of hopefully see things multiple times before you get to a quiz, right? Because the more times you see things, the better you learn them. So we're going to cover things in class or either in person like this or in recorded videos, which I'll show those in a second. Then like before you do homework, I'll typically, probably won't be every week, but a lot of weeks, I'll have something like this. So this is the participation number 1. This is like a pre-homework. And the idea is, again, to kind of have, it's not homework, but it helps you. Okay, so it jumped into the last time I took this and got this question wrong. So it will have homework-like questions. Maybe they'll be just like, it's designed to be relatively short. So this one, I would guess it'd be, something like maybe 20, 25 minutes, maybe 30 minutes. But that would be like 30 minutes max. At least hopefully. So you'll have questions and then either like, however you want it, however, like a normal quiz, there'll be something to answer. But if you get it wrong, there'll be some feedback on that. Like this one, for example, is asking about the physical state of water, whether it's a liquid, a gas, or a vapor-liquid mixture, or in this case, a saturated vapor, a saturated liquid. It's asking you things about the state. If you get it wrong, there's this, some description of how I'm thinking about the problem and how I'm kind of working my way through this. So I'll try to have either like, little screenshots like this or text or some sort of hints and kind of immediate feedback for one, that your answer is wrong or that it's right. And then either way, have some kind of feedback for how I'm thinking through the problem. So hopefully it's like a first check for homework so that you make sure you're thinking about the things right, getting the right answer, stuff like that, before you dive into the homework. So this would be like after you've done the lecture stuff and after you've watched the lecture videos, this would be the first thing to dive into. Just as kind of an initial check that that's all making sense and that there aren't any questions on that. These typically you'll have 2 chances to get the right answer. And if you get the answer wrong, you still don't get 0 points. So you'll get like, half credit or 3/4 credit for the problem, even if you get it wrong, just by like, I went and tried it. But if you just go through and guess, you'll lose points on the thing. So they're designed to be relatively like, if you go and do it, you'll all end up with close to 100% or 95% by the end of the semester, but kind of a first check for some of that before launching into the homework. I won't do this every week, but for this week, I have an example of a couple example questions for the quiz, as well as solutions. If you want to go through that and see what kind of questions might be on the quiz, what would those look like? So that's there. Here, the chapter 2 homework problems, that's the scanned pages from the book if you don't have your book yet. After homeworks are turned in, I'll post homework solutions like this, which again, whenever you get your grade back on your homework, if there are things that you did wrong, this is hopefully a good resource to be able to see how I try to do a better job. I don't always, but I try to do a better job than like just book solutions, walking you through how I'm thinking about the problem. That's especially helpful in some of the later stuff that we'll do, more like in the next couple of weeks. Things get to be a lot of different steps. So I'll try to show like how I'm thinking through the steps and what the process that I use to solve these problems, what that looks like. So anyway, so this is what it will look like for, I guess this is homework number 1. Okay, so this class is, I guess on your syllabus, it's a 2-credit class. So we have an hour for 50 minutes of in-person, and then the other hour is virtual. So what the virtual stuff will look like is going to be kind of a mixture of things. I consider it a mixture of like the participation stuff, quiz stuff, lecture videos, kind of things besides homework that I'm asking you to do outside of class. It's going to be in like a normal week less than what it is this week. And I'll explain that in just a second. But what the pre-recorded lectures, at least what those will look like. You see there are 4 of them this week, but there won't be that many in future. But a lot of times there'll be a link to a YouTube video. If you want to look at that, we don't need to go through it and listen to myself. But basically what's happening in the YouTube video, I'll have a skeleton of notes, which I'll have posted so that you can take that and pull it up, print it off, do whatever you want with it. And then during the video, I'm going to talk through it and fill out my skeleton of notes. I think that helps make it a little bit shorter so that I don't have to draw every single thing. It also allows me to put, like diagrams and figures and stuff like that in there, so that we can go in and draw on the figure this part, and so that's how I'm going to typically do those videos. Is we'll have kind of the skeleton of notes, and then my idea is that you would have that somehow in front of you, whether it's on a computer or print it out, and then be able to mark those up and take notes along with me while we're doing it in the video. So I don't know. Hopefully my goal is that takes, instead of like a 25-minute video, it's more like a 15-minute video, because I don't have to draw out every single thing, and you don't have to draw out every single thing. So I think that's most of the stuff. I guess let me dive back into the syllabus for just 1 second, and then we're almost done. So the other thing to note about the syllabus, this last page here is our course schedule. Right, because this semester we have kind of a shorter semester than normal. That's why I said week 1 has more outside of class stuff than other weeks will. That's in part because I assume that some of your other classes will not do that right at week 1, and that you probably have less stuff to do this week than you will week 13. So I want to let's get that out of the way. So it will be just know the amount of outside of class stuff that we have this week is like a class and a half instead of just 1 class. So that's what I'm thinking. It's probably about double what you should expect normally, but this will kind of get us up to speed so that next week we'll really be able to dive in some more, what I think is more interesting stuff. The other things to note, so the schedule is tentative. It tries to, right, you can see, let me get my pen. You can see we jump around a little bit. It tries to say where in your book we're actually, pulling that material from, because we are jumping around a lot. The things to at least chisel in clay tablets, because they probably won't change, but maybe they could, is the midterm, right, on October 8th. That's probably when the midterm is going to be. There's probably going to be more changing and shifting of exactly what topics we're going to cover on what days, but the midterm probably will be October 8th. So if you want to put that on your calendar and figure out what that's going to look like for you. I think that's it as far as dates. Their final is then already November 19th. Okay, so if you can give me 5 more minutes. Again, I apologize for going over today. My goal is to really try to keep it in the 50 minutes, but I also want to keep, because we're doing recorded lectures, I need to keep all of the classes in the same lined up. And I guess, unfortunately, I have more time, so that I know you guys don't have a class after this. I'll try to respect that 50 minutes. Okay, so the last things, the help sessions are 7 to 9 p.m. Tonight there is a help session if you wanted to go and get started on things right away. The help session is going to be 7 to 8 p.m. tonight. They're, as of now, in person. There's some discussion about how exactly we want to do that, but as of now, it's going to be in person in the intro lab. And I'll let you know if there are going to be any changes from that. Okay, so we're going to talk this, like a lot of the lecture videos, I just want to give you like a quick intro of what those are going to be about so that you have some context for what the stuff is. We're going to be talking a lot about physical properties and phase diagrams and how do we know the properties of a substance. So we're used to physical properties or phase diagrams, something like this, right? A solid and a liquid and a vapor. Right? We consider this phase diagram, right? This is the same phase diagram, except it actually has temperatures and pressures on it. So I have here a fun demo. So this is a syringe. It has 5 milliliters of water in it. And then I plugged the top of it. So when I pull the bottom, right, super exciting. I have a super fun thought problem. That was really complicated and now a super fun demo. Okay, if I pull this, you see the bubbles? What are the bubbles? What are those bubbles made of?
Water vapor.
Water vapor. So I just boiled it. Typically, we think of boiling, right, in everyday terms as something getting hot, but obviously this didn't get hot. It's still room temperature, but it boiled because I reduced the pressure. Right, so on this phase diagram, you can tell that they're not air bubbles because when I let it go, right, there are no air bubbles left. It was sealed from the air. What happened? I went from a state up here, state A, where we were liquid water, and I went down by reducing the pressure, by pulling on this, to a point where now we are, right, in this case, we're a mixture of liquid and vapor. So now we're right here on this line at point B. Okay, one of the problems that we'll have, so this is the normal way that we think about phase diagrams. One of the issues with this normal way of thinking about phase diagrams is it doesn't contain enough information. Right? Point B, for example, there's no difference between when I first start pulling and there's just a little bit of water vapor and when I pull it a lot farther. Right? Those are both like exactly at point B, exactly on that line. So in this class, often we'll use and we'll look at phase diagrams that look like this. Instead of pressure and temperature on our axes, we have here pressure, and this lowercase v is specific volume. So that's the volume of the thing. So when I'm, again, now going from what I'm calling state A, where we just have liquid and I'm not pulling on things, as I decrease the pressure, I have to decrease the pressure quite a bit before, like I have to pull a little bit, which means I'm decreasing the pressure quite a bit before finally it actually starts to move. So that's what's happening. So this is me, I'm pulling, I'm pulling, I'm pulling, I'm pulling, I'm pulling. Finally, the plunger starts to move and our volume actually starts to increase. And then, right, I'm going from, like, the volume has increased a little bit. It went from 5 milliliters to 10 milliliters. It doubled. I can keep pulling, and now we're up to, like, 20 milliliters, and I'm increased the volume by 4 times. So you can look at this phase diagram and see now, okay, how much have I actually moved along this way? If I kept moving, eventually I'd get to this point over here, which would be, again, at the same pressure, but that would be where I would keep pulling and there would be the last drop of liquid would actually turn into gas. So this phase diagram has 2 sides. And again, we'll talk more about these in the videos, but this is like where the liquid first begins to boil. And on this side is where the last drop of liquid boils. So over here we have a gas, over here we have a liquid. In the middle we have a mixture, like I do right here, of both the liquid phase and the gas phase, and they're in equilibrium. It's like partially boiled. So that's what's happening under the curve. So we'll use these kinds of graphs a lot as we're looking at physical properties, and we'll get some more terminology to be able to describe exactly where we are on this phase diagram. But it'll take us a little bit to kind of get comfortable thinking in terms of this type of phase diagram instead of the normal phase diagram that we're used to. We're going to do that in at least really the first half of the course in tables, steam tables, which you saw in 150. We're going to do, so this first week is kind of a crash course in relearning steam tables. So hopefully you didn't forget everything about steam tables. If not, we'll catch you up to speed quickly. And figuring out, okay, how do you find exactly what the properties are if we know this temperature and this pressure, right? So if we have 500 degrees C and 100 kilopascal, this is the specific volume. That's how much space the thing takes up. And if we have a different temperature and pressure, we would have a different volume. We're going to try to correlate, like, what are the physical properties, temperature and pressure and volume of materials at different phases. We're going to use tables of data like this. And I'll say we'll use that for now. Eventually, right, we're going to treat these tables as a black box of magical information. They will not always be a black box of magical information, but they are for now. We'll eventually, really in the second half of the course, we'll build in some of the theory for where in the world do these numbers come from. Okay, there are multiple different types of tables. So the tables for saturated water. Again, if you think back to this kind of a diagram, we're going to have one set of tables which kind of covers this part, the liquid. We're going to have one set that covers the gas over here, and we're going to have another set that covers basically like this area. So we're going to have different tables for different areas on the phase diagram. It's going to take us some practice to be able to figure out how to navigate things and find, if I give you a certain condition, how do I find what phase it's in? Where am I on the phase diagram? And where do I find it in the tables? And how do these things all line up? That'll definitely take some practice. So a big chunk of this first kind of the online portion of the class is figure out how do we navigate these tables, because we need to understand physical properties to be able to do anything more fun with it. So that's what this kind of you can expect to see from some of the online stuff this first week, is how do we think about this and how do we navigate phase diagrams for materials. A lot of what we'll do is water, but it applies to carbon dioxide and nitrogen and refrigerants and anything else that we might be looking for. So with that, I think we'll end for today. Like I said, you can find kind of the second half of the class. I guess it's like a half and a half. So the second, probably like full class, and some of the different activities and stuff on Moodle. I'm going to try to post, I will do it. I will post like a little one-page bullet pointed kind of like note document on this is how we're doing different parts of the class, just as like a reference guide, because I know you all are taking a whole bunch of different courses and everything is different than normal, and all of them have all kinds of different how we handle everything. So hopefully it'd be like a little short. A lot of it's in the syllabus if you have questions about things, but this will be like a little short one-page bullet point. This is how we're doing different things. So look for that. I'll send out an email shortly after class. All right, that was a lot for the first day. A lot of that kind of hoopla. So hopefully next week we'll be able to jump in and do some more actual thermodynamics than we did today. But I hope you guys have a great weekend, and we'll see you all next Thursday. Thank you.
Thank you.